So I'm going to take this next part of the video and talk about the last portion of everything that I haven't covered in any of the videos for chapter 6. And I'm going to start with talking about exercise 25 from checkpoint or from section 6.1. And 25 looks like this. What we have is a system of equations that asks us to solve it by doing the following. We are asked to solve this system. It says 1.5x plus 0.8y equals 2.3. Then we have 0.3x minus 0.2y equals 0.1. Now I'm going to talk about something a little bit different. I'm going to talk about elimination and how you deal with solving something using the elimination method. And the way you go about doing that is I need to get these two, it doesn't matter which variable, but I got to get something to line up. And the way I'm going to do that is I'm going to take this second equation and I'm going to multiply it by 4. Now you might say, well, what do I need to multiply that by 4 by? Well, what I'm going to do is I'm going to create a new equation then by doing this. And what I get is 1.2x minus 0.8y equals 0.4. Now, as you can see, this and this match up, but they're complete opposites of each other. So that means if I add these two things together, these two equations, I get a third equation that's in the system, and this second variable, the y, eliminates. So this variable is gone. That means I can solve this for y, or excuse me, for x. So I divide by 2.7. I just got an email. So x is equal to 1. And you can plug that in to find y. Doesn't matter which equation I plug that into, but you can plug that into any equation you want to and find out what y is equal to. I can plug it into the first one. I can plug it into this one. I can plug it into this new one that I created. Now I'm going to talk about exercise 31, and 31 looks like this. It says x squared minus y equals 0, and 2x plus y equals 0. Now, what we have to do with this is we have to solve something for a variable. It doesn't matter what we choose, but I'm going to solve this by moving the y to the other side, so I get x squared equals y. Now, wherever I see y, I'm going to replace that with x squared. So what I actually have is, if I replace this here with x squared, I have x squared plus 2x equals 0. So what I need to do with this is I need to solve this. Now, it's a quadratic. You can do one of three things. You can complete the square, you can factor it, you can use the quadratic formula. I'm just going to factor it because it has a GCF of x. I'm multiplying two things together to get 0. One of these two things is going to be 0. Either x is 0 or x is negative 2. So my answer is actually going to have two ordered pairs. So you have to plug in both to figure out what y is. Now, from a graphing standpoint, what this looks like is we have a parabola and we have a line going through it. So we have the line intersecting the parabola at two different points. We just have to figure out what those 2 points are. We have the x coordinates. Now we just need to plug in the y to find the y. Again, 33 is very similar. I'm going to set it up, but it's the same idea. So I have this system I'm going to solve for one of the variables. It doesn't matter which one. I'm going to move this y to the other side, so I get x equals y minus 1. So you might say, well, where do I plug that in for? Can I plug it in for something? Well, the answer is yeah, you can plug this in for x in the other equation. The only problem is that you're going to get something that looks like this. And you have to solve this now. Well, you can square something, and that means you have to take y minus 1 times y minus 1. So that's what this looks like. So I got to go through the process of solving this whole thing. So I get, and I'm going to move this up to here, I get y squared minus 2y plus 1 minus y equals a negative 4. So if I combine like terms, I get y squared minus 3y plus 1 equals a negative 4. If I add the like terms to the other side, if I add 4 to the other side, I get y squared minus 3y plus 5 equals 0. Now we have a problem with this one because this one is infactorable, so you're going to have to do a little bit more work to get the answer for this one. Okay? So you have to go about this a little bit differently. But if you are curious as to what the answers are for this one, you have to solve this for y. You can use the quadratic formula. You can't factor it. So what are your two answers? Well, we get negative b, so that's 3, plus or minus the square root of b squared, which is 9, minus 4 times a times c, so that's 4 times 1 times 5, all over 2 times a, or 2. Hopefully you can see here that that's going to be the square root of 9 minus 20. So you get the square root of a negative 11. That is a problem. You have no real solutions. So what this means is you have a parabola and a line that never hits it. That's what that means. You have a line and a parabola that never meet. So there's no solution for this because you get a square root of a negative number. And you would have to use the quadratic formula to figure this out. Okay? It's not going to come easy to figure out that that's the actual answer unless you get to this point and use the quadratic formula. So I'm going to talk real quick about these types of problems, and I'm going to use elimination. You can use substitution, but I'm going to show you what happens. Again, we have this system, and I'm going to get these variables so that they match up. So I need to times this first equation by 2. So I get 2x minus 4y equals 6. And as you can see, I'm no longer going to use this. This is my new equation in my system. So if I add these two equations together, I get negative 2x plus 2x, that's 0. Negative 4y and a positive 4y is 0, equals 7. Now, you might look at that and say, that doesn't make sense. 0 plus 0 does not equal 7. Well, the reason that this happens is because when you have a system of equations, from a graphical standpoint, we are talking about two lines that meet somewhere. And we're trying to find that point where they meet. And sometimes we have two lines that don't meet. So what is the case for this? If they don't have a point where they meet, they are parallel. So there is no solution. So this is an example of something where this doesn't happen. The two lines are parallel. Now you might look at this and say, well, is that always going to happen? Is there always going to be one or no solution? Let's multiply this by 2 and see what happens. You're not always going to get something that multiplies by 2, but you're going to get 4x minus 2y equals 2. Now this is the exact same question or equation with just the scale factor of 2, but if you notice they're the exact same line. Now if I draw the same line in the plane and just draw it twice, and I try to subtract these two things, I get 0 plus 0 equals 0. Well, that's true, but that doesn't tell me anything about what the solution is. Well, the solution is where they all meet. And if the line is the exact same thing written twice, all the points on the line are solutions. So there's an infinite number. Because it's the exact same line. The last problem I'm going to look at is how you deal with a word problem. It says, a plane flying into a headwind travels the 2,000-mile flying distance between these two towns in 4 hours and 24 minutes. On the return flight, the same distance traveled is 4 hours. Find the airspeed of the plane and the wind, assuming both remain constant. Well, we have a distance and a rate and a time. The distance is 2,000 in both cases. We know that. Okay? The only difference is that we have a different rate both times. The first rate is 4 hours and 24 minutes. So 4 plus 24 over 60, which we have to reduce. And that reduces to, so this is a time, and this reduces to 4.4. And we have a rate. So there's my first equation. Then our second equation is 4 times r. Now you might say, well, I have two equations with two different r's. Well, we have to know exactly what r means in both of these. This is the rate against the wind. This is the rate with the wind. So the way that we deal with this is that this is the plane with the wind taking away it. This is the rate of the plane with the wind added on. So really what our two equations should look like are this. And if you distribute these out, you get a system of two equations. That looks like this. And you can solve this the exact same way that we've solved them before. Using substitution, elimination, it doesn't matter. But you'll get a system, you'll get a equation to find the speed of the plane. And this is the wind speed.